We're going to get started. Okay, so as Anil mentioned last time, we're going to start talking about graphs. We're going to have a few lectures on them, in fact. Yeah, so this is an example of a graph. They're one of the most ubiquitous concepts in all of computer science. Like maybe half of all computational problems involve a graph somehow, so it's a good topic to talk about. All right, so what is a graph? That's what we're going to be trying to answer today. But I think maybe the real question is, what isn't a graph? As I said, they come up in all kinds of problems in computer science. So let's see some examples. All right, so there's Zuckerberg talking about Facebook. And this is a great example of a graph. You can kind of see an illustration of it behind him. So this is a graph where the vertices or the nodes are people, and the edges are like the friendships between these people. So this social network is a very large graph. In fact, I guess he likes to boast about how large it is. So when he's giving this talk, the number of nodes or vertices is like 10 to the 9. And maybe the number of edges or connections is like 10 to the 12. So that's a very nice, large graph you might want to run an algorithm on. Here's another example, even larger actually. The World Wide Web. So here's actually a picture of a research paper about the link structure of the World Wide Web. So maybe you can kind of tell a little from this diagram. The vertices in this example are the pages on the internet, and the edges are the hyperlinks, where one page points to another. And this is actually an example. I'm going to define all these terms eventually, but this is an example of a directed graph, one where the edges have like a direction. They go from this page to that page. Unlike in Facebook, where it's assumed that friendship is a symmetric relationship. This paper is from 1998. It's written by this guy, Larry Page. It's about PageRank, which was like the algorithm that the proto-Google used to get good web search results. It's called PageRank. You would think because it's about ranking pages, but actually it's because he just named it after himself. So it's a little hard to count how big this graph is. In this 1998 paper, he said there was like 150 million nodes, pages, and 1.7 billion edges or links. These days, I guess it's kind of hard to count, right? Because in the olden days, maybe there's a concept of a web page, but now like they're maybe automatically generated. It's hard to count, but maybe it's something like 1 trillion web pages and 10 trillion hyperlinks, something like that. So that's a very, very large graph. Another very large graph that gets used a lot in computer science applications and real-world applications are street maps. You go to like Google Maps or like Yahoo Maps or whatever to find the shortest route between point A and point B. Somehow over the last year I got used to using Yandex Maps, so it has very good traffic information. In this example, you might think that the vertices are like the intersections between roads, and then the edges are streets. So would that be an undirected or a directed graph? Yeah, it's like mostly undirected. Usually you can drive both ways on a street, but maybe since there's some one-way streets, right, maybe it's directed. I couldn't estimate how large these graphs are, but they're like similarly gigantic. Now, not every graph is a gigantic graph with like billions and billions of nodes. Here's a famous graph called the Zachary Karate Club graph. So it was like in 1977, this anthropologist called Zachary, he studied, I guess that's what they do. They study people, right? He studied this karate club at like a university in the Midwest with like 34 people in it. And he like drew like the social network. Like he like visited them and talked to them, and he like decided to like put an edge between two people if they had some kind of relationship or friendship. And like he made this graph, and it's like a very famous graph in social science research and anthropology research. And what was cool about it is he actually ran some computer science algorithms. He's an anthropologist on this graph, and it was like 1977, but he ran like this Ford-Fulkerson algorithm on it to try to infer some things about the social structure of the graph. And actually, it's a funny thing, like this karate club, it had like this one sensei or whatever, but like not everybody liked him, and there's some kind of like backstabbing and stuff, and it eventually like split into two like rival karate clubs. And somebody talked about like predicting that this could happen based on the link structure of the social network. So this is like a famous example in anthropology. It comes up a lot, and then people in computer science nowadays like to study social networks and large networks a lot. So somehow this example is talked about a lot, this small graph. Actually, it's talked about so much so that there's in fact a Zachary Karate Club for like, if you give like a talk in computer science about Zachary Karate Club and use it as an example, then you can belong to this club and you can get this Zachary Karate Club trophy. So I'm hoping that will happen to me this year. Okay. What other examples can you have? Well, they come up in every, parts of, I don't know, in vision or graphics. So like, images are often naturally represented with graphs. So I just got this off the internet somewhere. So here the vertices are just points and the edges make this triangulation. This is maybe a medium-sized graph. I also didn't count, but maybe n is 1,000 or 10,000. I don't know. This is also an example of something called a planar graph, which is something we might study later in this class. It's a graph where when you can draw it in such a way that the edges don't cross each other. It also comes up in some places, as I said, in computer science where you wouldn't expect. So here's a little example. I'm not going to get into it too deeply, but I'll say it anyway. There's something called the register allocation problem in compilers. So maybe a compiler encounters some code that's trying to compute an arithmetic expression, like I think this eventually computes minus a minus b plus d, and it uses 5 variables. And the compiler has eventually got to turn this into machine code, and like somehow the instructions are faster if you do the computations using these registers rather than memory. And so you might want to try to pack all of this into like as few registers as you can so it can be done very quickly. And so you need to look at this code and figure out, is there a way I can do this without remembering all the variables? Maybe I can remember only 4 of them so that everything can be done with registers. Okay, so this is the kind of stuff they thought about in compiler theory in like the 70s and 60s and so forth. And there's apparently a big breakthrough in 1980 by this guy who's sort of famous for other reasons, Chaitin, who was working at IBM at the time. And he had this fairly simple idea to like make a graph out of it. So he's like, let's say you've got some code like this, make a graph where the variables are vertices, and you put an edge between 2 vertices if these variables like need to be alive at the same time. And then somehow he showed that the least number of registers you need has something to do with the graph theoretic properties of the graph. It was like the chromatic number of the graph, whatever that is. And people were very excited about this and happy, and it like made them compile to faster code and so forth. So as I said, I don't even know if I got this example right. I got the variables are the vertices. I'm not sure I did the edges correctly for this, but something like that. So he had the idea you convert the problem into a graph, and then you can do some graph theory algorithms, and it'll tell you something about the problem you want to solve. Okay, so somehow the life lesson of these little examples is that if your problem has a graph in it, like you're very happy because that's the greatest object ever. If your problem doesn't have a graph, you should try to make it have a graph somehow, like if you can. It's really genuinely a good strategy. Okay, so now we will start to talk about graphs. And I have to warn you, the remainder of this lecture, it's the graph theory 101. It's like 100 definitions. I think I'm literally not exaggerating. Maybe you've seen them before, like a million times. If so, like you can play Candy Crush or something during this lecture. Or maybe this one. This is a very fun graph theory related game. If you've seen them 0 times before, then I'm sorry, there's like 100 things to remember. Hopefully, like most of you are like, I've seen them maybe a few times before, not totally sure about all of them, and so you'll be the perfect audience for this lecture. Okay, so definitions. What is a graph? Okay, so I'll start with some pictures. This is a graph. Graphs look like this. That was like the Facebook example. But then we were like, well, actually, there's a more complicated thing. Sometimes it's directed graph where the edges have directions. They're like arrows. So because of that, sometimes you call this object an undirected graph. Now there's like a third category, which is, I guess it's usually called general graphs. They can also be directed, but I gave an undirected example here. And that means they have these other features, like more than one edge between 2 vertices. That's called parallel edges. Or they have this thing, which is like an edge between a vertex and itself. That's called self loops. I also call these annoying graphs because it's kind of annoying to deal with them. Like sometimes you actually want to have them in your problem, and it's good to know that they exist, and sometimes you want to use them, but it also makes all the explanations like more complicated if you're always having to worry about like, oh, are there self loops and so forth. So we mostly won't stick with these graphs. And in fact, this is like an annoying situation. Because these graphs exist, these graphs are sometimes called simple undirected graphs to distinguish them from general graphs. And it's this weird situation. There's this concept called a retronym, which I can explain like this. Like, there used to be this thing in life, and that was called a guitar. Okay? And then, like in the 40s or whatever, they invented this thing, and that was called an electric guitar. But then they had to go back and now call this thing an acoustic guitar, because to distinguish it from this, which, I don't know, I mean, these guys are cool and all. But it's a similar situation here. Like, you can imagine these graphs saying, like, why should I change my name? He's the one that sucks. So for this reason, I mean, I think he has a good point. So for the rest of this class and in general, we're going to call these objects graphs. Okay? And if we want to allow directed graphs, we'll say so. And if we want to allow general graphs, we'll say so. So for now on, graph means an undirected graph like this, which I haven't defined yet, but that's what I'll do now. OK. So here's finally the definition. It looks very mathematical, and you see there's not even any pictures in it. But a graph, G, is a pair, V and E. V is the set of vertices, also called nodes. Those are totally synonyms. There's no difference between a vertex and a node. Sometimes you just get bored of saying one or the other. And E is the set of edges. So V is just a set. That's the vertices. And E is a special kind of set. I mean, each edge in E, little e, is itself a set. It's a set of two elements, each of which are distinct vertices. Okay, so the edges are sets of two vertices. So here's an example. The vertex set is V is 1, 2, 3, 4, 5, 6. And this graph has 5 elements in its edge set. It has 5 edges. 1 and 2 are connected, 1 and 4 are connected, and so forth. Now that looks a little bit mathematical. So indeed, we usually like to draw these things. So the picture of this graph would be here. Okay, so I mean, you have one circle for each node, and the lines are the edges. Okay, some notation that's like very, very, very commonly used. We almost always write n for the cardinality of V, the number of vertices, and we almost always write m for the number of edges. Okay, and so much so that like we might not always even mention it. I mean, like you should mention it if you're writing your homework, but usually if it's an unspoken situation, then that's what n and m mean. Okay, so I mean, there's the formal definition. It's worth looking at, yeah, exactly, haha, edge cases. Yeah, it's looking at some graph theory humor. It's worth looking at, some special cases of this definition just so that we're on top of things. So can we have a graph with no edges where m equals 0? Yeah, I mean, you can. There it is. For example, the vertex set is 1, 2, 3, 4, 5, 6, and the edge set is empty. So the picture is, that's the graph. Now, it's kind of a weird graph, but, it's allowed. This is called the empty graph with 6 vertices, or n vertices. We'll even see it come up in a proof today. OK, let's take it to the next level. Can we have a graph with no vertices? Well, if you look at the definition I gave, it's actually OK. I just said the vertex set was any finite set, so it could be empty. But I drew a picture of it here, too, by the way. It's kind of like very annoying to allow that as a graph. In fact, there's a very famous paper. This person, Frank Harari, is like one of the most famous graph theorists in history. And Reed was famous, too. They wrote a whole paper on this exact question called, is the null graph a pointless concept? Null graph is the graph with no vertices. And that's even like a joke, because in the olden days of graphs, they called vertices points sometimes and edges lines sometimes. So that's a joke. Is it a pointless concept? Anyway, it has a very nice abstract, too. They say we discussed this graph critically. Arguments for and against it are presented. There's an extensive survey of the literature. And at the end, it's like, no conclusion is reached. You can kind of tell they don't like it, though. And in fact, we're going to say no. OK? For this class, we'll say no. You cannot have a graph with no vertices. We'll always require that the vertex set is non-empty. OK? So that's to take care of that edge case. But one vertex graphs, that's totally allowed for sure. N equals 1. There's a picture of it, and that's called the trivial graph sometimes. Okay, more definitions. There's a lot of words in graph theory. So let's say you have a graph and you have some edge E, which is the set U, V. It's connecting U and V. Here are like 4 synonyms for the same concept. So we say that U and V are the endpoints of E, U and V are adjacent, U and V are incident on E, U is a neighbor of V, V is a neighbor of U. So sometimes you can kind of guess what it means based on the word, but these are some words you'll often see. Yep?
Do we use that same terminology if it's a directed graph?
Yeah. Although, yeah, then you need to invent a word which is not really settled for, like, if you have an edge, like which one is like at the head and which one is at the tail. So you could say head and tail or source and destination. It's a little bit more annoying when it's directed graphs. Yeah, so speaking of this neighborhood stuff, here's another term for you. If you have a vertex in the graph U, then n of U is called its neighborhood, and it just means all the vertices that it's connected to. Notice that does not include itself if you have a simple graph, which we usually do, because there are no self loops unless we allow it. So here's a graph below, and I just gave some examples. The neighborhood of Y is V, W, and Z. The neighborhood of Z is Y. The neighborhood of X is empty, and so forth. And we're also always often interested in the size of these neighborhoods, and that's called the degree of the vertex. So the degree of a vertex U is the number of neighbors it has. So here, like the degree of Y is 3, the degree of Z is 1, the degree of X is 0. Okay, so we've done 20 definitions, so let's do a theorem. This is probably the most basic theorem in graph theory. It's a very cute theorem, sometimes called the handshaking theorem, but I just call it by its content. It says that suppose you have any graph and you do the following thing. You add up all the degrees of all the vertices. Then you get 2 times the number of edges. Okay, that's the theorem. So I'll prove it to you. Here's an example. The one we saw, so I just wrote in yellow the degree of each of the vertices, 2, 2, 0, 3, and 1. And we can check, if you add them up, you get 8. And that indeed is 2 times 4, the number of edges. Okay, so this theorem has a nice proof. And here's how you could imagine this proof. Instead of writing in yellow the actual number for the degree, let's just put like a little dot or a token just to count the number of degrees. So this one has degree 2, this one has degree 3, this one has degree 0. Just put some tokens there. And now just tell each vertex to put a token on each of its edges, right? So we gave it 1 token per edge, so it should be able to put exactly 1 of its tokens on each edge. I'll show you that again. Oops. So they go. And now, after you tell them that, each edge gets exactly 2 tokens. So on one hand, the total number of tokens is the sum over all vertices of the degree, because that's how many tokens you gave out. But at the end, each edge gets 2 tokens, 1 from its 2 vertices on which it's incident. So on the other hand, there's 2 times E, cardinality of E tokens, so that gives you this equality. And this kind of proof is a classic proof strategy. It's called double counting. Like you introduce some object, and you write down 2 different ways you can count it up, and then you deduce that those 2 counts have to be the same. Any questions about that proof? Well, it's kind of by a picture. I mean, maybe as I was writing it, I would write it like this, but it's the same thing I just said in words. So this is how you might write such a proof. Just write what I said. Okay. Let's ask a few basic questions about graphs. So let's say you have an n vertex graph. How large can m be? In other words, what's the maximum number of edges? Can somebody say? That is, I got the correct formula, but maybe there's a conceptual way to say it. Yeah?
I would like to choose 2.
Yeah, n choose 2. Because there are n I mean, it's the same as the formula that was given here. There are n vertices, and like, you know, for each pair of them, pair of distinct ones, you're allowed to have an edge. So if you have all the possible things, that's n choose 2. Okay, and that's n times n minus 1 over 2. Okay, which is a half. That's what you said. That's a half n squared minus a half times n. So you could, if you're being a little bit sloppy, say that's big O of n squared. And that's a good thing to remember. The number of edges is at most quadratic in the number of vertices. It's even smaller than n squared, actually, but it's O of n squared. So for example, here's a graph where n is 5. And this is when you put in all possible pairs, I mean all possible edges. You go for all 5 choose 2, which is 10 edges, and you put them in. And this kind of object is called the complete graph on n vertices. When it has all the edges, and the notation for it is k sub n. Like that's the name of this graph. Well, this is k sub 5. I don't quite know why it's the name. When I was a kid, I learned that k is the first letter in complete in German. But then I was reading on Wikipedia that they don't even call it the complete graph in German, so they don't know what it. Anyway, it's k sub n. Okay, I want to also mention a definition, which is not really a real definition, but it's a good terminology anyway at this point. This is bogus, but if you have a graph where m, the number of edges, is kind of order of n, you usually call that a sparse graph. So like the number of edges is like kind of a constant times n. And on the other hand, if m is kind of close to the maximum, like if it's omega of n squared, you say that g usually say it's dense. Now, this does not actually make sense because, I mean, this O notation and omega notation only makes sense if you have like a function of m, like you have like many different objects, one for each n. And if you just have like one graph with n is like 100 and m is 1,000, it doesn't make sense to ask if it's big O or big omega of anything. So that's why I say it's a bogus definition, but still, I mean, it's just informal terminology that's very useful. I mean, if you have a graph where like there's not too many edges compared to the number of vertices, you say it's sparse. On the other hand, if it has lots and lots and lots of edges, like kind of close to the maximum, you say it's dense. And you know, it doesn't even cover everything. Like if the number of edges is like n to the 1.5, then I don't know. It's neither, maybe. Okay, let's go back to talking about this complete graph, k sub n. Has an interesting little property. In it, every vertex has the same degree, which is, yeah, n minus 1. That's the maximum degree of any vertex in a graph. N minus 1, at most you can be connected to all the other n minus 1 vertices. That's called a regular graph. So it's another piece of terminology to remember. In particular, you say a graph is d-regular if every vertex has degree d. Okay, so some kind of simple examples. Kn is an n minus 1 regular graph. And the empty graph, where there are no edges at all, is 0 regular. Every vertex has degree 0. Okay, so let's talk a minute about this d-regular graphs for other values of d, more interesting values. So we'll start small. What about d equals 1? So what could a 1 regular graph look like? A graph where every vertex has degree 1. Well, you say, well, let's say we have some vertices, and now I need every vertex to have degree 1. So like, okay, vertex 1, it's got to have one edge coming out of it. So I don't know, maybe it goes to 6. And now actually 6 is done, right? It's supposed to have exactly one edge, so it's sort of taken care of. And maybe you're like 2's got to connect somewhere, so maybe 7. And now these guys both have degree 1. And now these guys both have degree 1. And these guys have degree 1. And that's it. And it's not hard to show that actually, I mean, you can kind of see, right? It can only be like this. Basically, you have a collection of edges that don't touch each other. In particular, that's only possible if v is even. Actually, is there a way we could have known in advance, based on something we talked about, that if you have a 1 regular graph, you have to have an even number of vertices? There was a theorem we proved about degrees of graphs, yeah?
It would be 2 times E would be all the degrees.
Yeah, the theorem was that the sum of the degrees is 2 times the number of edges. Wait a minute, does this work?
I think so.
Yeah, so then 2 times the number of edges would have to be n, because each vertex, of which there are n, have degree 1. So n is 2 times the number of edges. So particular n would better be even. And you see that that's true. And that indeed, there's always n over 2 edges. Okay, this kind of graph is called a perfect matching. That's another term. A matching means you have like a bunch of edges that don't touch each other, and the perfect means that like every vertex is involved. So it's just everybody has like one match. Okay, so 1 regular graph's cool. We did it. What about 2 regular graphs? So let's try the same. I mean, this is just exploring graphs and a way to introduce some definitions. So I don't know, we'll write down 8 vertices and say, okay, you know, vertex 1 has got to have degree 2. So let's just, for fun, arbitrarily pick 2 guys to connect it to. Now you look at 3, you're halfway done, right? It has 1 edge, and it needs to have 2 edges coming out of it. So maybe 3 might connect to 4. And then 4 is kind of halfway done too. It has 1 edge coming in, so it needs to have another edge as well. Maybe it connects to 6. 6 you could connect to something else, but you could also maybe connect it to 5, hypothetically. And actually now this piece is done, right? All the vertices here have degree 2. So then you would say, okay, let's keep going. Maybe 2 needs to connect to 2 other vertices, and then if you do this, then you're done. Every vertex had degree 2. It's also not hard to see, I mean, if you play around with it for a minute, I mean, this is kind of the only thing that can happen. So this object is called a 5 cycle. This object is called a 3 cycle. And it's not too hard to see that if you have a 2 regular graph, it's going to be a disjoint collection of cycles. So like, you know, it's kind of forced. Okay, any questions about that? Okay, let's go to 3. What about 3 regular graphs? Well, the long and short of it is there are many, many, many possibilities. I mean, for 1 regular and 2 regular and 0 regular and n minus 1 regular, we could exactly figure it out. 3 regular graphs, I mean, you already entered like an enormous world of possibilities. I mean, there's a zillion pictures I could have drawn here. Here are 2 examples. Okay, so there's no real way to classify them. I mean, there's lots of possibilities. Okay, I mostly want to talk about graphs, which means undirected, simple graphs. But you know, directed graphs are also an important concept, so I'm going to say a few things about them. Okay, first, directed graphs have one of these celebrity couple style portmanteau nicknames, like, you know, who is this? Come on, you guys don't know who this is? Kim Ye. Kim Ye, thank you. And for the older people, this one? Gradually, oh, okay, so you do read the gossip pages, good. Yeah. Yeah, and similarly for directed graphs, they're called digraphs. So that's an example here. So now an edge, it's not a symmetric relationship anymore, right? Like an edge goes from one vertex to another vertex. So you can represent it by an ordered pair. Okay, so this graph is, you know, it's got 5 vertices, p, q, r, s, t, and like this edge is p comma q, this edge is p comma r, etc. Okay, and notice over here we have an interesting situation. There's an edge from s to t, which is s comma t, and also an edge from t to s, which is t comma s. Okay, and those count as distinct edges, and they're okay. You're perfectly allowed to have that in your directed graph or digraph. So now, getting back a little bit to the question here from Will, there's different concepts of degree now, because you know, basically at a vertex, there's 2 things that can be going on. You can have edges coming into you and edges going out of you. So we call the out degree of a vertex the number of edges coming out. So, or in this more symbolic terminology, the out degree of u is the cardinality of the set of all v's, such that uv is an edge. And conversely, the in degree is the number of edges you have coming into u. Okay, so in this graph, the out degree of p is 2, and its in degree is 0. If we look at s, for example, it has 1 edge coming out, so its out degree is 1, and its in degree is 2. Actually, I didn't put this in the slide, but suppose I took a digraph and I added up the out degree for each vertex. I went through all the vertices and added up all the out degrees. What would I get? That's true. It would be the same as the sum of the indegrees. And in particular, it would be, we both said it here, it's the number of edges, right? Because that would be like single counting. If you sum up all the out degrees, it's kind of like for each vertex, you kind of charge each edge to one vertex, but it's sort of uniquely charged to the vertex it's coming out of. You could think about that in your spare time, if you missed it. OK, so let's talk about another topic, since this is a computer science class. We need to store graphs on computers. So how can we do that? It's a little tricky, maybe because usually we're used to drawing pictures of them, right? But eventually they have to go down into some data structures. And there are two traditional methods for doing this, called adjacency matrix and adjacency list. And to describe them, I'm going to assume that you're storing a graph whose vertex set is just the numbers 1 through n. You can just rename the vertices if that's not the case. And I'll always use this little graph as an example. OK, so the adjacency matrix representation is a matrix. It's a two-dimensional array that's n by n. N is the number of vertices. And you put either 1s or 0s into it. And in the ijth entry, you put 1 if vertex I is adjacent to vertex j. And you put 0 if they're not adjacent. Okay, it's a pretty simple concept. So this graph looks like this. And for example, this row is the second row. So it's talking about vertex 2. This means that 2 is connected to 1. This means that 2 is not connected to 2. 2 is connected to 3. 2 is adjacent to 4. Okay, so in graphs, simple graphs, for example, you'll always have zeros on the diagonal because there are no self-loops. And it'll also be symmetric across this diagonal because aij will always have the same value as aj, because in a usual graph, I is adjacent to j if and only if j is adjacent to I. So this is a nice format, and it's also good for the other more general graphs. So for example, if you have a directed graph, then the definition is you just put a 1 if I going to j is an edge, like I comma j is an edge. OK, and in that case, it might not be one of these symmetric matrices anymore, because you can have an edge from I to j, but you don't necessarily also have to have an edge from j to I. And for general graphs, these graphs where you can have like more than one edge between vertices, you can just, instead of putting 0s and 1s, you can put like natural numbers, which represent the number of edges from I to j. And that could also have numbers on the diagonal, because self-loops would be allowed. OK, any questions about this concept? OK, so that's one way you can store a graph. So it has some pros and cons. So can somebody suggest a pro? Yeah?
Efficient to tell if there's an edge between two vertices?
Yeah, it's very efficient if, like, you say, I wonder if this graph, vertex 7 and vertex 11 are connected. It's easy. You just go to the 7, 11 entry and see if it's 1 or 0. Yeah?
The Legate transformations that are caused by the adjacency matrix really interesting properties of the graph.
Yes, very good. So I was going to say just that. I'll put it up. This is the first thing that was said. You can easily check if a vertex is present or absent. This is another one. It's very simple. You just make a matrix. That's very nice. And this suggestion was that, once you have a matrix, maybe you can do something involving linear algebra, if you love linear algebra like I do. And that's actually a very fruitful idea. Linear algebra and graph theory are like best friends forever. So we're even going to talk about that in a later part of the class. Not today, but a later lecture. Yeah, so it has some good pros. What about some cons? Downsides? Well, you already gave one. Yes? I was actually, what were you going to say?
Oh, I was going to say so.
OK, so two suggestions. It's very, it's very space inefficient, because it always uses pretty much exactly n squared memory, right? Because you make an n by n matrix. And sometimes that's OK, but it can be very wasteful if you have a sparse graph, where m, the number of edges, is a lot less than n squared. OK, so if you imagine the graph of Facebook, where n is a trillion, you're not going to want to store that with an adjacency matrix, because then the size is a trillion squared. That's very large. So that's a downside. Any other downsides? I mean, that's pretty big, but yeah.
Half of the matrix is redundant.
Yeah, that's all. I mean, if it's a normal graph, then yeah, half of the matrix is kind of redundant because you know it's symmetric. That's another wasteful aspect of it. Yeah?
If you want to go through all of the edges coming out of a certain node, you have to spend that.
Yeah, you guys are very good this morning at like knowing exactly what I was thinking. Like, there are many possibility things I could say, but I was going to say exactly that, which is that, one common thing you want to do when you're working with the graph, let's say you're hanging out at vertex 7, you want to know, okay, who are the neighbors of vertex 7? And, maybe for some graphs there might be like 5 neighbors, but in this representation you kind of have to go through the entire row to like look for those 5 ones. So that could take like order of n time. Okay, so pluses and minuses. The other traditional way to store graphs is like an adjacency list. So that's a different kind of data structure. So it's a bit more complicated. An adjacency list starts with an array of length n, one for each vertex. And in the ith entry of this array, you store a pointer, or like a list of the neighbors of I. So I'll try to draw a picture here. So the adjacency list is an array, size 4 in this case, and each entry in the array holds a pointer to a list of the neighbors. So this says that like 1, maybe this is like a linked list, for example. 1 is connected to 2 and also to 3. 2 is connected to 1, 3, and 4. 3 is connected to 1, 2, and 4, etc. Okay, so there's also some pros and cons of this. So can somebody suggest some pros? Or a pro? Yes?
Is it sufficient to get the neighborhood vertex?
Yeah, that last thing we talked about, if you're at a vertex and you want to know, like, okay, who are the neighbors of this vertex? It's right there. I mean, you just go to that entry of the array and like look through the list. So that's good. Any other ones? Yes?
Takes up less space.
Yeah, it takes up less space in general. Like, how much space does it kind of take, roughly? Yeah? Oh, the what? Yeah, I mean, the size of roughly it looks like the number of edges. Actually, it's arguably a little bit more than that. Like, imagine the empty graph, for example, yeah? Yeah, it's more like m plus n, which, well, I'll say something in a second. It's very space, so these are the two main pros. Yeah, it's very space efficient. The memory usage is something like order n plus order m, because basically you kind of have like one node in this bunch of lists for each edge. Actually, each edge appears sort of twice in a way, once for each of its endpoints. So that's order m, but you also always have this vertex array of vertices of size n. So it's order n plus m. I will say, though, that like most of the time in life, it's kind of weird to have a graph where there are fewer edges than vertices. That's kind of unusual. So mentally, you should think of m as usually at least to n. So this is, usually you just think of it as like order m, like was suggested, but technically you have to be careful about it, because you could have some weird graph with very few edges. And the other thing that was mentioned is, yeah, it's very efficient to run through the neighbors of a vertex u. You can just do it in order degree of u time, which is the best you could hope for. Cons? Downsides? Yep.
Very annoying to code.
Very annoying to code. It's certainly worse than adjacency matrix, yeah. It's not so bad if your language has built-in list structure, but if it doesn't, then it's probably annoying, yeah. Someone else? All right, well, I'll ask you again, yeah?
To check if an edge exists, you have to walk through vertices.
Yeah, this thing that was really good for adjacency matrix is bad here. I mean, if you just want to know, hey, is there an edge from 7 to 11? You have to go to 7. Depends if there's so or not. If you want to ask if there's an edge between 7 and 1,000,000, you have to go to vertex 7 and maybe go through the entire list looking for vertex number 1,000,000. And this could be as bad as order of n time. Okay, so both of these have some pros and some cons. Are there any other possibilities for how to store a graph on a computer?
Probably.
Did you say probably? Yeah, sure, indeed. Do you have a suggestion?
You could just naively model it as a bunch of pointers, objects that are constructs, vertex being next to it.
Yeah, you could have it more like I guess really like a linked list where the nodes are nodes and you have pointers. You have to be a little bit careful though, because you need, say a node has you need to know how to get to all of the nodes, Like, for example, especially if you have like a node that's not connected to anything, you need to know about it. So it's I think it would kind of come down to something like an adjacency list, that idea. Maybe. Other suggestions? Yeah, you have a suggestion?
Yeah, store it as edge-centric, and then do the node construction.
Yeah, I'm not exactly sure what you said, but it is true that, like, for example, the adjacency list is sort of vertex-centric. Like, I mean, you have the vertices are the real objects, and then they sort of store their edges. You can imagine, like, maybe having an array of the edges, and it could store what vertices it's connected to. Anything that, like, might fix some of the problems we were talking about? Does somebody back here have a suggestion? Yeah?
Well, I mean, if in your adjacency list, if you did sort them, like you said, that would fix the inefficient lookup problem for a single edge.
Well, it wasn't quite right.
Well, you can do binary search.
You can't do binary search with a plain linked list, right?
Well, okay, no, you'd have to do a few modifications, but theoretically.
Yeah, well,
I'm sure this is for area research or something.
yeah. I mean, you could put like a different data structure than a list. Like, I don't know how much data structures you've seen. I mean, I guess not too much necessarily, but you could have like a binary tree or something, data structure, or a hash table or something like that. So I just want to say, like, adjacency matrix and lists are like very classic ways to store a graph. Like, that's how they did it in the olden days. But you can do something cooler, right? I mean, you don't have to always do adjacency matrix or list. Like, a good idea is to have an adjacency list so that you can have all these nice properties. The only bad property of it, right, was it's a very long time to look up whether an edge is present or not. But you can put like a hash table in there too.
You also can't do linear algebra with adjacency lists.
Yeah, so that, I mean, adjacency matrices are better for like the linear algebra. That's more like theoretical analysis of graphs. But yeah. Okay, so just be thinking what you can do in your data structures and algorithms classes. All right, time for more definitions. So we're going to talk now about connectedness. Okay, so here's a graph. There it is. That's maybe similar how you might store on a computer a bunch of numbers. Does anybody notice anything peculiar about this graph?
Odds connect to odds, evens connect to evens.
Yeah, that's true, actually. I didn't notice that. Very good. Yeah. Well, it's hard to notice something peculiar about it when you don't draw it, right? But yeah, very good. It's disconnected. Actually, that you can tell from this odds connected. Oh, that's cool. I like that. Yeah, you can tell from that odds connected to odds and evens connected to evens that it's disconnected. I was just going for the fact that it's disconnected, which is totally obvious when you draw it, but then it's not obvious when you're just looking at the edges. And in life, in computers, for example, you just get it written more like this on your computer, right? So it tells you that there's something a little non-trivial about connectedness or non-connectedness. So this is called a not connected graph. So this whole object is one graph. It just happens to not be connected. Okay, so terminology. Here's an example graph. Actually, how should we define when a graph is connected? Can somebody suggest a definition? Somebody in the latter, backer half? Come on, you got to be able to suggest a definition for when a graph is connected. Yeah?
The adjacency matrix is regular.
If the adjacency matrix is regular, do you mean if the graph is regular?
Oh no, by regular means it's a full graph.
I'm not sure. I kind of doubt it, but maybe. Yeah? Yeah, this is what I was going for. If there's a path between any two nodes. Okay, so, well, yeah, we'll get to that. What is a path? So, yeah, normally you say a graph is connected if for all pairs of vertices u and v is reachable from u. Well, then you say, well, what does this reachable mean? You just defined one thing in terms of another. So we say a vertex v is reachable from u if there's a path from u to v. Okay? And, well, we still have to define path. Actually, I slightly prefer to say this. This is totally fine and correct, but I would slightly prefer to say that v is reachable from u if there's a walk from u to v. So now we have two undefined terms, path and walk. Path is like the obvious, it's what you would guess. But let's start with walk. So a walk in a graph is a sequence of vertices 0, 1, v0, v1 up to vn, n is at least 0. Just as so every 2 consecutive vertices are an edge in the graph. Okay? So we say it's a walk from v0 to vn, and we say its length is n. That's the length of the walk. It's the number of edges traversed. Okay, so in this graph, like p, q, s, r, p, r, s, t is a walk from p to t, and it's of length 7. Okay, so we said u is reachable from v if there's a walk from u to v. So is u reachable from u? Yes, because you're allowed to have walks of length 0 if you look at this definition. Anyway, we count u as being reachable from u as always. Okay, and now a path in G is just a walk where no vertices are repeated. And it's not hard to see that if there's a walk from u to v if and only if there's a path from u to v. So if there's a path from u to v, then there's definitely a walk from u to v, because a path is just a special case of a walk, one where you don't repeat any vertices. On the other hand, suppose you have a walk from u to v, so it goes around and maybe it visits some vertex many times, and then finally it goes to its destination. You can just cut out all the repetitions, basically. I mean, that's called shortcutting. Let me give you a little example. We saw this walk that went p, q, s, r, p, r, s, t, went from p to t. You can just say, well, s got repeated here. We can just delete all this stuff and only go to s once. So that's called shortcutting out this part, and it reduces you to just the path p, q, s, t. Okay, so v is reachable from u. That means there is a walk, and there's also a path from v to u, from u to v. And we define the distance of u from v to be the length of the shortest path from u to v. So in this graph, the distance from p to r is 1. Even though there's this length 3 path, it's not the shortest one. Distance from p to s is 2, p to t is 3, distance from p to p is 0, etc. Okay, more terminology. We kind of saw this one before. A cycle is a walk of length at least 3 from a vertex to itself, but where the only repeated vertex is u. Or basically, it's like a path, plus at the end, you have that last edge from the beginning to the end. Okay, so maybe the words are more complicated than the picture. Like this PQRSP is a cycle of length 4. Okay. So this 5-vertex graph is connected. Every vertex is reachable from every other vertex. Here's a picture of a graph with 11 vertices, and it's a disconnected graph. Because I don't know, S is not reachable from U, for example. What we say about this graph, because it kind of looks a bit like 3 graphs, we say it has 3 connected components. So this is a connected component, this set of vertices is a connected component, this set is a connected component. I guess you kind of see what I mean. The connected component of S is all the vertices that are reachable from S. There's another way to define it if you remember some formal math terminology, which I'll do for kicks. We have this notion of U is reachable from V, and it's an example of what's called an equivalence relation. You might know to check if something is an equivalence relation, you have to check 3 things, right? You have to check that a vertex is reachable from itself. That's true, kind of by definition. You have to check symmetry. If U is reachable from V, then V is reachable from U. That's true. You can just do the path backwards. And this one is called transitivity. If U is reachable from V and V is reachable from W, then U is reachable from W. That's true because you can go from first W to V and then V to U. That might give you a walk instead of a path, but that's okay. Okay, so then you might know that if you have an equivalence relation on a set, the vertices, it divides the set elements into groups, subsets that are all equivalent to each other. And those are the connected components. So that's one way you can define it. Another way you can define it if you want. Any questions about this? Okay, let me say a little bit more about digraphs because there's one somewhat tricky thing that's going on here related to walks and connectedness and so forth. So in a digraph, a walk, you mean the succession of vertices, it has to like follow the arrow. So like it has to be you have to have a directed edge where like all the directions are going the same way. So like P, R, S, T is a walk, but like, P, R, P, Q is not a walk because the arrows have to go in the same way. So once you make that, all the definitions before, like reachable, walk, path, cycle, it's all the same definitions for digraphs. There's one catch, though, from a couple of slides ago, which is that now this reachable from is not a symmetric relationship. You can have that U is reachable from V, but V is not reachable from U. Right? So T is reachable from P. P, R, S, T is a walk from P to T, but P is not reachable from T. Because once you're at T, actually, you cannot have any walks except just the length 0 walk that starts at T. So in particular, that kind of screws up a little bit the definition of components, connected components. So usually the only thing we say about digraphs is this notion of strongly connected components. So we say a graph is strongly connected, or a component is strongly connected if all pairs of vertices can reach each other. So, but there you need like the paths going both ways. So here, yeah, this is not strongly connected because T cannot reach P. Okay, let's pause, and now we're going to introduce some other terminology based on a little game. Let's say I ask you, make an n-vertex graph connected using as few edges as you can. Okay, so let's think about how we might do this. Well, let's start small with n equals 1. Well, we're done. It's connected. We just need that every vertex is reachable from every other one, and there's only one vertex here, and it's reachable from itself.
We're starting with no edges.
Yeah, let's imagine like this game where like you start with no edges, and you're like, I got to keep adding edges to make until it's connected, and try to use as few edges as I can. Okay, so here we did it with 0 edges. Let's say n is 2. Well, it's not connected so far, so we better add at least one edge. There's only one choice, and now it's connected. So that was also easy. One edge is necessary and sufficient to make it connected. Let's go up to 3. That's also pretty easy. It's not connected. If you just add one edge, it's still not going to be connected, right? Because the one vertex you don't involve will be disconnected. But also, no matter how you add 2 edges, it's going to become connected, because it's going to look like this, or a rotated version of this. So 2 edges are necessary and sufficient here. It's a little pattern, but it gets a little bit different in the next step. Say you have 4 vertices. Well, 1 and 2 edges are not going to do it. You can kind of check. But you can do it with 3 edges, something like this. Now it's connected. And you can do it in a sort of a fundamentally different way as well. This is another 3-edge, 4-vertex graph, which is connected. It's somehow not fundamentally the same as this one. On the other hand, it doesn't always work. So you can have a 3-edge, 4-vertex graph like this one, which is not connected. But anyway, for n equals 4, 3 edges are necessary and also sufficient to make it connected. So there's still some kind of pattern, right? You can probably guess the pattern. It's that n-1 edges are necessary and sufficient. So the sufficient part is not that bad. So the fact that you can always connect up a n-vertex graph using n-1 edges is not hard. You can do it in a couple of ways. You can take one vertex and connect it to everything. That's n-1 edges. Here n is 9, I think. That's called a star graph. Or you can just make it a path. So this also has n-1 edges if it has n vertices. That's another way you can do it. You can also do it in some other way. This is like another example. Okay, so you can always do it with n-1 edges. And the somewhat trickier thing, it's not actually super easy, is to show that you always need at least n-1 edges. If you only use n-2 edges, then it can't be connected. So we're going to prove that. And we're actually going to use a lemma to prove it. So here's what the lemma says. It's actually not that complicated. It says, suppose you have a graph and it has k connected components. And now, suppose you change it by adding a new edge in that wasn't already there. So you connect some u and v that weren't already connected. Then the new graph has either k or maybe k minus 1 connected components. That's the lemma. So basically, the number of connected components when you add an edge can stay the same or can go down by 1. You may already see how that's going to help us prove this fact, but let's talk about the lemma first. So, okay, let's say you've got some graph G. I didn't draw all the nodes. It's kind of like a abstract version of the graph with k equals 3 connected components. Okay, so these guys are all connected. These vertices are all connected. These vertices are all connected. And now I'm going to add an edge between two vertices u and v that wasn't already there. And there's going to be two cases. Case one is that u and v are in different connected components. So now I add an edge. And now how many connected components are there? 2, yeah. And in general, it's going to go down by 1 because you took 2 previously unconnected components, and now they're connected. Everything in here can now reach everything in here by first reaching u. That's because we assumed this was connected. Then going to v, then reaching anything in here because this one is also connected. Okay, case 2 is that u and v were in the same component. So maybe this is the picture. We add this edge, and now how many connected components will there be? Yeah, still k, still 3. Because, you cannot, you didn't connect any of the other two components. So you still have k components in this case. And that's it. I mean, it's not a very complicated lemma. That's just the two possibilities, and that's why it's going to be either k or k minus 1 after you add an edge. I do want to add a comment here, though. There's a little bonus observation you can make when you're thinking about this lemma. And it's actually this. In this case, too, I claim that when we add an edge from u to v, we actually create a cycle in the graph. Because, see, u and v were in the same connected component by hypothesis of case 2. So that means there was a path between them. And now we add an edge. So now it makes a cycle. OK? And once we notice that, we can also go back to case 1 and say, I wonder if we made a cycle in that case. And actually, you see that you don't make a cycle in this case. So why is that? Well, suppose adding this edge made a cycle. It would have to make a cycle involving u and v, right? Because, I mean, otherwise, adding this edge is irrelevant. So you would have had to have, like, if this created a cycle between u and v, it must have been that, it finished some path that was between u and v. But there's no path between u and v because u and v are, by assumption, in different connected components. OK, so everybody, any questions about that? Yeah?
So are we assuming that each connected component isn't complete?
Yeah, we don't necessarily assume that. So when we say connected component, it just has to be connected. So every two vertices in it are reachable from each other. It doesn't have to be like a complete subgraph.
Right, but we couldn't add an edge if it were a complete subgraph, right?
Yeah, so I mean, when I'm talking about this lemma, sort of the assumptions of the lemma are this new edge from u to v didn't previously exist. Yeah. OK, so let me extend this little observation because it kind of, now we know it's not just that when you add an edge, the number of components is k or k minus 1. We kind of have a way to tell if it's going to be k or k minus 1. Well, one way is if u and v were in the same connected component, it's k. If they were in different connected components, it's k minus 1. But we could also say that if a cycle got created, then the new graph will have k connected components. And if no cycle was created, then you're in the k minus 1 components case. OK. So I hope you can still read it. Let's go back to proving the theorem that if you have an n-vertex graph and it's connected, it has to have at least n minus 1 edges. Actually, does somebody want to suggest the proof based on even just the first part of this lemma? How can we show that if you have an n-vertex graph and it's connected, it has to have at least n minus 1 edges? Yeah?
Suppose you start with an empty graph.
Yeah.
You start we have n connected components.
Yeah.
We start adding edges. Each time we get at most one connected component off.
Yep.
Our goal is to get it down to 1, so we need at least a -1 step.
Yeah, perfect. That's right. So let me say what was just said. Imagine a process. Let's say you have some fixed graph G. You don't know how many edges it has, but whatever it is G, imagine this. Like, you have G. Imagine just temporarily taking away all the edges, and then you're going to start putting them back one by one. Okay? So you have some fixed G that's connected. You take away all the edges, but then you're going to start putting them back where they were one by one. So when you take all the edges away, then you just have n vertices, and each one is only connected to itself, so the number of connected components is n. Now we start putting G's edges back one by one. And the lemma tells us that every time we put back an edge, the number of connected components can only go down by at most 1. So it cannot go down too fast. But we're also assuming the original graph, or the graph you get when you put all the edges back, is connected, which is the same as saying it has one connected component. So by putting these edges back in, you have to go from n connected components down to one connected component. You can only go down by 1 at each step, so you have to have at least n minus 1 steps. So there has to be at least n minus 1 edges. Any questions? Okay, so that's that. Now, there's also this bonus feature to the lemma about cycles we mentioned, and let's look a little bit more carefully about how, so that's the end of the proof, but let's look a little bit more carefully about how it, might add something to this fact. You see, you might ask yourself, okay, we know it's possible to do it with n minus 1. We know you need at least n minus 1. You can also do it with more than n minus 1. You might say, like, what happens? I mean, what are the cases when you do it in exactly n minus 1? Well, suppose you want to connect it with exactly n minus 1 edges. It means that in this process, when you're adding the edges back, you have to go down by 1 every single time, because otherwise you can't get from n connected components down to 1 in n minus 1 steps. So it has to be that every time you add an edge, you're doing this part of the lemma. Going down by 1, which means you're never creating a cycle. Okay, so if you think about it for a second, if you're going to do it with n minus 1 edges, you can actually never create a cycle as you're going, which means that the graph has no cycles. That's our 100th definition, maybe. No, there's more. It's called an acyclic graph. And you can also see conversely, if you have more than n minus 1 edges in the graph, then at some point you'll have to have done this step where it doesn't go down, and you must have created a cycle. So this is like an if and only if. Okay, so a connected graph has exactly n minus 1 edges, if and only if it has no cycles. Does anybody know the name of this kind of graph? A connected graph with one less edge than vertices, and it's acyclic? Yeah, it's called a tree. Yeah. So you might not have thought of trees in that way. Let me draw a picture, sort of. So these are all tree graphs. They're graphs with some number n of vertices, and the number of edges is exactly n minus 1. And actually, we kind of sort of proved a theorem, which you can also make into a definition. And it's kind of interesting. So you can say a tree is any graph that has at least 2 of these properties. So we started by thinking about connected and n minus 1 edges, and we saw actually that also implies that it has no cycles. And if you kind of go through everything we talked about, you can just see that any 2 of these implies the other third one. So it's connected and it's acyclic. That means in this process, you could have only added n minus 1 edges. Otherwise, you would have made a cycle. Okay, so a tree is any graph with 2 of these 3 properties, and it will also have the third property too. So maybe if you're looking at the picture, you don't want to count things, right? So the easiest ones to check with your eyeballs are that it's connected and it has no cycles. Okay. So it's a little funny. We talked about binary trees in lecture 2. So it's sort of the same concept, but let me make some definitions here. So let's say you have a tree. Well, a leaf means a vertex of degree 1. So this tree has 5 leaves. And an internal node is all the other nodes, degree more than 1. So this one has 4 internal nodes. And then there's a concept of a rooted tree. So a rooted tree just means you have any tree, and then you just pick one vertex and say, that one's the root. Okay? And you can pick any vertex you want. So you could pick vertex 8 and say, this is a rooted tree. It's a tree, and 8 I'm calling the root. So you might say, why do you do that? It really basically mainly affects how you draw the tree. So if you have a tree, you can draw it like this. But if you have a rooted tree, you kind of always draw it with the root on top and like the rest of the stuff sort of hanging down by gravity. So I could not do the animation, but look at this tree very carefully. That's how you draw it as a rooted tree. So 8 is on top. And you see, it's the same graph, right? 8 is connected to 5 and 9. Yeah, 8 is connected to 5 and 9, and then 5 is connected to 1, 4, and 6 as well. 1, 4, and 6, and then it's the same graph. Okay, but this is how you would draw it as a rooted tree, where you just say 8 is the root, and you put it on top. And then once you have a rooted tree, there's more definitions. Basically, use all the terms you used in like talking about family trees, except that there's no like marriage. There's only one sex. So you talk about, 5 is the parent of 4, and 4 is the sibling of 6, and 5 is an ancestor of 2, and so forth. So that's some terminology used when talking about rooted trees, which come up a lot in data structures. And finally, we already had this definition in lecture 2 of a binary tree, but it's the same concept. A binary tree means a rooted tree where each node has at most 2 children. So in lecture 2, we defined it with some axiomatic or deductive system, but this is another way to define the same concept. Okay, any questions? Okay, so that's a lot of definitions. So there's not that much time left, but let's do a little bit of computer science before we go. So I'm a little excited because out of all the computational problems, all the algorithmic tasks, and all of computer science, I honestly, genuinely have a personal favorite. This is true. It's this one called max cut. Okay, it's the algorithms problem, which I love very much. So I want to tell you a little bit about it. Okay, so what is the max cut algorithmic problem? It's about graphs. The input is a graph. Good. And maybe this graph. And the output is a 2 coloring of V. What does that mean? It's just your algorithm has to give a color to each vertex, either, let's say, yellow or blue. Okay, so you just output like maybe 1 is yellow, 2 is blue, 3 is yellow, etc. But what are you trying to do? Like, what's the point? You have this goal in life, which is you want to have as many cut edges as you can. We say an edge is cut if its endpoints have different colors. So you think of maybe like you divide the vertices into the yellow team and the blue team, and like a cut edge goes between the 2 teams or color classes. Okay, so you're trying to find a coloring that makes as many cut edges as you can. Is that clear? Okay, so at first you might say, why would you want to do this? Well, is this a very fundamental algorithms problem that comes up a lot in computer science and in life? For example, here there's 5 cut edges. See, they go between yellow and blue. There's 1 uncut edge, this one between 3 and 5. Out of curiosity, would it be possible to cut all of the edges in this graph? No, why not? The reason is there's no way you could do it even just on these 3 edges. If you just even look at these 3 edges, no matter how you color them, you're going to have 2 that have the same color, and so you won't cut that edge. Yeah, it's an odd cycle. That's true. Okay, so yeah, where does this come up? Okay, for example, let's say you're the producer of a TV show with N castaways. And let's say you know the social networks of friendships between them. That's good. So maybe it's like there's 5 of them, and you know who's friends and who's enemies. And you have to divide them into 2 tribes, the yellow tribe and the blue tribe. And of course, what are you trying to do, right? You're the producers. You don't want to put the friends together, right? You want to separate them because you want drama, right? So you want to produce 2 teams or 2 tribes to maximize the number of broken friendships because you don't want the friends together. Yeah, drama lemma. So actually, the motivating examples might here be more natural if, when you're talking about social networks, instead of putting an edge between 2 friends, you put an edge between 2 enemies. That would be more natural for these examples. So you might want to record enemy ships. Actually, there's an app for that. It's called Enemy Book. It was invented by a theoretical computer scientist called Kevin Matleff. He's a nice guy. And yeah, its slogan is, it's an antisocial utility that disconnects you from the people around you. Okay, so you can see that, like, in fact, it would be kind of cooler if you had, when you have vertices, if you had the enemy ships rather than the friend ships, right? Like, if you go back to this Zachary Karate Club example, if these represent the enemies, then actually the max cut question is like, how would you partition these into two sets of vertices or Karate Club members so that as many enemy ships are broken, which is kind of like putting the people that like each other together. And in fact, if Zachary had run like had the enemy ships and run the max cut algorithm or a max cut algorithm on this graph, it really might have helped him predict exactly how this schism into two rival karate clubs would have happened.
Do a min cut on the friendships?
Yeah, you could also do a min cut on the friendships if, I wanted to talk about max cut though. Yeah, that's true. Okay, so now I definitely should get this trophy. The Karate Club trophy. Okay, so that's max cut and why you might be interested in studying it. So let's try to come up with an algorithm for it. I mean, you got this graph, you got to like divide the vertices into two colors to break as many of the edges as you can. What can you do? So we're going to see an example that uses kind of a generic computer science strategy called local search. It's kind of, but not quite like a greedy algorithm, which is another kind of a generic algorithm strategy we'll talk about next class. This one was invented by Sania and Gonzalez, an Indian guy and a Mexican guy in the 70s. And here was their idea. This is the algorithm. Let's say you're given any graph G with n vertices and m edges. You got to output some kind of two coloring. So the first step is just start with any two coloring at all. It doesn't matter. Just call them all blue, for example. Okay? And then you do a loop where you just keep trying to make it better, where you just try to have more edges be cut. So how do you do that? You do it in like the most simple way. You just go through all the vertices U, and for each vertex U, you look at it and say to yourself, if I switched U's color, would that increase the number of cut edges? Okay, and if you find such a vertex, then you're like, okay, I do it. I switch its color and increase the number of cut edges. And then you keep looping. Then you just go back through all the vertices again and say, now if I switched a vertex color, would increase the number of cut edges. Okay, and you just keep doing that and doing that and doing that. And if you go through all the vertices at some point and you never find one which would make the number of cut edges go up by switching its color, then you halt. And you just say, okay, this is the two coloring I'm going to output. Okay, does the idea make some sense? Yep.
Is this algorithm even correct?
Well, we didn't really define correctness in the algorithm. I didn't actually, this is a subtle point. I didn't actually tell you that you had to find the best cut. You didn't have to find the best partition. I just sort of defined it so far. We'll talk about this later. I just defined it as try to find a good partition, whatever that means. But there's another aspect of correctness as well, which is that you really want to make an algorithm that does not loop forever. So the first thing you might ask yourself is, does this algorithm even halt? It's not clear, right? Because you could imagine like, okay, you're going through the vertices, and then you find one where it's better to switch its color. So you switch it. And then you maybe switch another vertex color, and another vertex color. Now it might be better to switch this one back. And then now it might be better to switch this one back, and so forth and so on. So it does always halt, though. Can somebody say why it always halts? Yeah?
Because the very best you could possibly do is to have every single edge cut.
Mm-hmm.
And every time you switch a vertex, it has to be increasing the number of cut edges by at least one.
Yeah.
And you can only increase by one so many times before you reach your fixed maximum.
Perfect. Exactly right. So every time you go through the loop and you like do something, the number of cut edges goes up by one because like you only like switch a color if that makes the number of cut edges go up. You cannot go above m, right? That's all the edges. So like you can only do at most m switches. Okay, so overall the number of loop iterations is at most m. And so you can use that to analyze the running time. Basically each iteration might take something like order m plus n time because you might have to go through all the vertices, that's n. And to figure out if it's good to switch a vertex, you kind of have to look at all of its neighbors. I don't want to be super careful about it, but this is definitely like a polynomial time algorithm because it has at most m iterations, and each one is kind of linear time in the size of the graph. I just want to emphasize that this is a polynomial time algorithm. Okay, so then you may want to ask yourself, is it a good algorithm? So here's an interesting observation about this algorithm. So let's say you run this algorithm, it goes for a while, and finally it halts. It has some 2 coloring. I claim that every vertex u, if u looks around to see how many of its enemies' ships got cut, it's at least half of its degree. So at least it's cut off from at least half of its enemies. So why is that true? Yes?
If it weren't true, then it would have been better for you to flip it, because then more than half would be cut.
Yeah, that's exactly right. Like this is somehow even exactly what you check when you're checking if it's a good idea to flip a vertex. If a vertex u has less than half of its edges cut, then it's better to flip it, right? Flip its color, because then when you flip its color, all the uncut edges will become cut, and all the cut edges will become uncut. So you always want that to be the bigger amount. Okay, so the final output will have this property, that every vertex has at least half of its own edges touching it cut. And as a conclusion, you can tell that the final coloring will have at least how many cut edges? This is kind of a little calculation for you. How many cut edges will it have by virtue of this fact? Yeah, it'll have at least m over 2. Half of the edges will be cut. Intuitively, you could say to yourself, well, if on each vertex at least half of its edges get cut, then it feels indeed that half of all the edges at least must have got cut. Another way you can do it, maybe I'll leave it as a little exercise for you, but you could try to count or double count the set of edges that got cut. If you add up for each vertex all of its cut edges, then that actually gives you 2 times the number of cut edges. Because for each cut edge, you counted it twice, once for this neighbor and once for this vertex. On the other hand, if you add up all the cut edges for each vertex, you get sum of all the degrees over 2. We know that the sum of the degrees is 2 times the number of edges, so that would give you the number of edges, and then divide by 2 for the double counting. Okay, so that's why I said you should think about it at home if you don't catch it. But it's not hard to show that this observation implies this conclusion. So this algorithm is actually, this is kind of good. I mean, this is nice. It always at least makes sure to cut at least half of the enemy ships. So that's good, or at least half of the edges. Now, you might further ask, is this the optimal algorithm? I mean, does it always find the best 2 coloring? The answer is, well, we'll see. Let me give you an example. The answer is going to be no, it doesn't always find the best one. This example I'm going to show works on any cycle that has a number of vertices that's a multiple of 4. So here it's 12. So maybe the algorithm picks some arbitrary coloring and it goes around for a while and it's trying to make progress. And maybe at some point it reaches this stage, yellow, yellow, blue, blue, yellow, yellow, blue, blue, etc. So far, which edges are cut? It's kind of like every other edge is cut. Right? So actually, so far at this point, it has exactly the number that we kind of expected, or that could be guaranteed. Half of all the edges are cut. But the algorithm, oh, there's a typo here. The algorithm doesn't just stop. It keeps trying to switch vertices colors to make more cut edges. But if you look carefully, no single color switch here is going to give any improvement. Basically everything's the same. Let's say if you change this to blue, then you gain this edge as cut, but you lose this one. So actually every switch doesn't change the number of edges cut. So the algorithm tries it all, and then it's well, nothing helps. I'll just output this one. But actually, what's the best number of edges you could cut here? Yeah, you can actually cut all of them. If you do alternating colors, you cut all of them. So even though you could cut all of them, it only gets half of that amount. So you can certainly find the best coloring by just trying all 2 to the n different colorings. Right? There's 2 possible colors for each vertex. You can just try them all, see how many edges it cuts, pick the best one. That's going to take you 2 to the n time, though, so it's very slow. So you might ask yourself, is there a better polynomial time algorithm than this local search algorithm? And we'll talk about this later in the course. Okay, so see you on Tuesday. And there'll be a new homework around noon.